So our next speaker is Professor Doina Precup from McGill. Thank you for coming.
Thank you very much for the invitation. I'm going to talk about deep reinforcement learning, but really in the context of building general purpose AI agents, and a lot of the thinking in this talk has been informed by the long discussions with Rich Sutton, as well as a lot of collaborators, both at DeepMind as well as at McGill University. So just to recap very quickly, reinforcement learning is a way of learning from interaction with an environment that's really been inspired by the way that animals learn. And so you can see there a little mouse that's doing reinforcement learning essentially by pressing levers, and we mimic this process in automated agents by allowing the agents to take actions in an environment, try things out, and receive numerical rewards. And the goal of these agents is basically to maximize the long-term return that they obtain. And of course, the poster child these days for reinforcement learning success is AlphaGo, and Oriol talked very eloquently yesterday about the program. But just to recap, this was very exciting because we had a program that learns from scratch and becomes better than people. Not only that, but it also invents new ways of playing. But on the downside, this is an environment that is in some sense very clean, right? So perception, it's very clear what perception is. It's just the state of the board. It's very clear what the actions are. They're sort of determined by the rules of Go. They're deterministic in their effects. The reward is also very clear. It's given only at the end of the game, so that creates some difficulty because the reward is delayed. But we don't have a problem trying to figure out what the reward function is. And so in this case, we have algorithm that actually works surprisingly well. A lot of my research has been driven by more complicated goals, such as making dinner. And for those of you who have families that need to be taken care of and you have parents that both work, this is actually a very complicated task. Which requires planning at multiple time scales. There are some things like strategic choices of what are we going to cook. There are some things that are just fine motor skills, making sure that nothing falls off the table. And then there's some things that are more like steps that need to be done, like mixing stuff, for example. And we learn how to do this. We learn how to do it efficiently from one stream of data. We tend to get better at these tasks as we go along. Actually, kids learn to do this pretty quickly. And we can also quickly adapt to new situations. So if an ingredient is missing from the house, you'll find some ways to substitute it, and usually it'll work okay. So that suggests a sort of continual learning paradigm where things are much more messy. Perception is more messy, rewards are more messy, and we would like to have forms of knowledge representation that support sort of this type of reasoning and this type of learning. So that's what I'm going to focus on, but I will use as a basis what we usually do in reinforcement learning. And if we take a closer look at what AlphaGo does, it has two kinds of knowledge representation inside. It has a policy, and we can think of this broadly speaking as procedural knowledge, how to do stuff. So the policy tells us what actions to take in what situations. And then it has a form of predictive knowledge, which is called the value function. And the value function estimates what is the expected return of the agent from different situations. And so AlphaGo uses both of these forms of knowledge, and in particular, it uses the prediction, the value function, in order to figure out how to modify the policy. And so what I'm going to be talking about is a way of building these two types of knowledge, procedural knowledge and predictive knowledge, in agents that are trying to do continual learning or lifelong learning. And when I say procedural knowledge, you should be imagining things like either acquiring skills, like, how do I rotate the wrist in order to mix up something, as well as goal-driven behavior. And in terms of predictive knowledge, I'm going to not be very ambitious and focus on things that are essentially acquired from interaction with an environment. So something like predicting the effects of actions, and if we want to be really ambitious, something like figuring out how the physics of the environment works, not in a formal sense, but in a sort of intuitive sense. And whatever form of knowledge representation we use, we have sort of three goals that would be interesting to achieve. One is that it should be expressive, that is, it should be able to capture knowledge about abstractions, things like objects and places and people, as well as knowledge about extended actions that take some amount of time until they complete. We would like this knowledge to be learnable, obviously, and ideally without close supervision. And we would like the knowledge to be composable. And what I mean by this is that if we have pieces, either prediction pieces or behavior pieces, we should be able to take them and quickly assemble a solution to a new problem without requiring the acquisition of large amounts of new data. And so those are the three desiderata that we're going to try to put into our representations. So in terms of procedural knowledge, there's a particular framework that I'm going to be talking about, which is called options. It's been around for about 20 years now. And the idea of options is very much inspired from previous work in both classical AI in terms of macro actions, as well as in, for example, behavior-based robotics and hybrid control. The idea is to have chunks of behavior that start, go on for some time, and stop. And so these three elements of an option are essentially an initiation set or a precondition that tells us how such a behavior starts, a policy, which tells us how actions are taken while the behavior is executing, and the termination condition, which tells us probabilistically how to finish the behavior. And so, for example, in robot navigation, you might imagine that a robot goes ahead if there is nothing in front of it and will stop whenever it detects another object in front of it. And so that defines for us initiation set, policy, and termination condition. And so we can think of options essentially as behavioral programs in the following sense. If you had such an option, you could imagine it to be a subroutine that gets called. While it's called, it's executing actions. And for this, it uses what we call state, that is whatever summary of the environment we have at our disposal, as well as possibly other local variables. So this might mean, for example, counting time steps since it's begun. So this encompasses open loop as well as closed loop ways of choosing actions. And of course, options can call other options, just like a function can call another function. And so you can imagine multiple layers in this hierarchy of behavior, even though in practice people typically use just 2 layers because that's kind of simple. The other thing that we can do is instead of allowing these functions to execute until completion, we can decide to interrupt them if there is something better to do. And so you can think of this as a particular form of concurrent execution where all the options are monitoring on the side if there is a better alternative, and if so, the behavior can switch. Now, one of the interesting questions is where do these options come from? And one way to think about this is we can give them by design, or we could associate them with certain sub-goals. If we have such sub-goals in the environment, for example, in a game, you might want to acquire certain objects or go to particular places. But in general, this is actually a very hard problem. Sometimes people sort of call this the representation discovery problem. We have a particular solution that we've been using which is based on policy gradient, because that was kind of easy to do, and we didn't have to invent other rewards. I won't dwell on the details too much. This is work of my student Pierre-Luc Bacon. But one of the things I wanted to show is that this actually brings us some quantitative improvements in Atari games over a state-of-art algorithm, and also some interesting qualitative results. So in particular, on the bottom here, there's some pictures taken from a game called Sequest. It's a game where there's a little submarine that has to go up for air and also rescue a diver every so often. All we ask is for our algorithm to create 2 options for this game, and we don't tell it anything else other than play the game and create them. And what you can see is that it creates 2 options. One corresponds to these white segments and one to the black segments. They are temporarily extended most of the time, so they take control for some time, and they essentially correspond to behaviors where the submarine is either going up for air or going down, so they kind of make sense. And the specific case where this is especially useful is in transfer learning. So this is a case where we're looking at a standard task called the 4 rooms. The agent has to navigate to a particular goal state. We train the agent to find the goal state, which is in here in the middle of the hallway, and then we move the goal state to a different random location, and we see what happens. And so what you see in these graphs is immediately after the goal moves, all of the agents degrade in their performance, but agents that use options actually recover much more quickly, whereas agents that only use single-step reasoning actually take a long time to recover. So this is all kind of exciting, but it doesn't tell us anything yet about predictive knowledge. And so we need to pair this idea of having procedural knowledge to predictive knowledge, and we're going to use the inspiration from the value function in reinforcement learning to do that. And so just to quickly recall, a value function is just the expectation of the long-term return. And there's really two things that are of interest here. One is the reward. That's the signal of interest. We're going to think of it that way. Typically in reinforcement learning, we consider it a scalar. And then we have a discount factor here, and that essentially tells us the time scale over which we're trying to predict or we're trying to optimize behavior. And so the particular way in which we use value functions is in some sense driven by computational constraints. And these equations that we have allow us to use some great computational tools like bootstrapping, which comes to us from dynamic programming, as well as sampling in order to estimate expectations. And so we would like to have agents that use value functions, but that predict about many different things. And this is just a picture from Adam White's thesis that shows a lot of these predictions. So these are all signals that are collected from a very simple robot, a Roomba-like robot, but that has sensors on top of it. And you can see that there's a wealth of information that comes at all kinds of different timescales, and we would like to have a way to capture this information and learn it from just a single stream of experience. And so to do this, we can use a straightforward generalization of the idea of value function, which I'm going to call generalized value functions, for lack of a better name. And the idea is that instead of rewards, we're going to think of having a cumulant function, C here, and the only difference compared to rewards is that this might output also a vector or a matrix or something like this. It's still going to get combined additively over time steps. And then we're going to have a continuation function, and this continuation function essentially tells us what's the probability of continuing a trajectory at a given state. And now this can become state dependent. And so the idea really from this type of representation is actually very old. It's been inspired by the pandemonium architecture of Oliver Selfridge. But it's been developed over some number of years in collaboration with Rich Sutton's group. And the original paper was called the Horde architecture. And the idea is that you're going to have many of these value functions that are learning predictions at different timescales about all kinds of things from one stream of data, and we're going to leverage well-known off-policy learning algorithms from reinforcement learning to do this. So we think of these generalized value functions essentially as building blocks of knowledge that take as inputs whatever we're trying to accumulate, the continuation function and some policy or way of choosing actions. They can estimate values at a particular state, and they output this estimate. And so as a result, you can imagine that you can take these and, for example, take the estimation of one generalized value function and use it as part of the input for another value function, or perhaps as part of the cumulant for another value function, and we can kind of hook these blocks up together to build more complicated representations. And so one particular case that's been of interest that I'm just going to show for concreteness is the case of option models. So option models have also been around for a very long time. They're kind of paired with options, and if you think of an option as a behavioral program, you can think of its model essentially as modeling the expected reward and the distribution over the next state, which is the semantics, right? What will happen? What will be true after the option has executed? But of course, these models are predictions about the future, and so since we think of predictions as captured by value functions, we're going to try and see if we can capture these models as value functions as well. And the interesting property of models that we would like to preserve is one of compositionality. So these are just some results that basically show that if one has models that are, for example, for a sequence of options, these can be constructed from pieces of models of the different options. And this is done just by some simple linear algebra. It's not done by learning or by a fancy algorithm. It's essentially a zero-shot computation. So the main question then becomes, if we have an option, can we actually learn how to model that single option. And then compositionality will take care of doing this when we have many of them. And so for this, we're going to look at the anatomy of the reward option model. And that's just like a value function. It's got rewards here going while the option is executing until it terminates. And so we can actually write down Bellman equations for this model. And they look just like value function Bellman equations for those of you who are familiar with reinforcement learning. They have a reward part. And then they tell you that from the next state onward, if the option will be continuing, we will receive the remaining rewards. Okay? And the only difference is that continuation is now given both by the environment allowing you to continue, that is, you live to see another day, as well as by the option deciding that it wants to continue, which is this term 1 minus beta omega of S prime. And this term, interestingly, is now dependent on state. So that is the place where this is now generalizing from the usual reinforcement learning framework, where we think of discount factors as being fixed and given somehow part of the problem. But in this case, in fact, we can think of this discount factor as being under the agent's control, and we can even think of learning it from data, learning appropriately how to discount and when to terminate. But of course, this is just a value function. And so, in particular, it's a generalized value function, and we can do the same kind of trick for the option transition model. In fact, we can do it for many different things, including some known hierarchical reinforcement learning frameworks like feudal networks, as well as some other recent algorithms like value transport and auxiliary tasks. So this is kind of cute. It's an interesting insight. The question is this useful for something? And so in order to show that it is useful, we actually rewrote policy gradient, which is a very well-known reinforcement learning algorithm, in this framework of generalized value functions. And the math is not really particularly important, but essentially it says we can think of the gradient of a value function as a generalized value function with a very particular kind of cumulant that takes into account the gradient of the log policy. And so because this is a generalized value function, we can think of independently estimating it in some other way from data with its own function approximator. And the effect that this has is essentially to help us reduce the variability in the behavior of usual policy gradient algorithm. And so in this picture here, these green bars are this idea of using essentially two independent estimates for the general value function and combining them. And we're comparing that against usual policy gradient across a wide range of parameter values, learning rates, specifically, and what we see is better stability. So we're not trying to do something better, we're just trying to do something more reliable. And we can do this type of reasoning also in Atari games. Here, actually, we're hooking up multiple value functions in a sort of cascade, each of them being parameterized and using output computed by the previous value function. And we're comparing, again, performance in Atari games. And we can see that, that our algorithm is actually performing better both on the entire Atari game suite, which is shown here, and significantly better on some of the games. So it seems that this kind of way of building predictive knowledge is actually empirically good and useful. So this brings me to a point that's going to connect to the theme of this session. What I told you so far is just methodology, right? How do we build deep RL agents that look like real AI agents? But of course, if we imagine these agents as living for a long time in some environment, then really there's not one task that they have to solve. And the way that we typically evaluate reinforcement learning agents is through the lens of having one task and having a return and trying to improve on that return. So that's one number. And a lot of the time, the evaluations that you see in papers are of the form, my number is bigger than your number, therefore my algorithm wins. And I've showed you some of these evaluations as well. We're all, in some sense, guilty of this. And sometimes we do qualitative analysis, right? We look at the behavior, we see what the agent is doing, what kind of trajectories it's producing, and we might get some conclusions out of that as well. But really, there's another question that we kind of need to address, which is this agent actually preserving knowledge well? And is it enhancing its knowledge as it's going along? And this is a problem that is difficult. The answer to this question, unfortunately, is not as simple as saying, well, we're going to do better empirical methodology and we'll make all our code open source and we're going to do experiments that improve reproducibility. This is inherently a problem of what are we trying to measure? How are we trying to look at our agents and through what lens? And so one question is, can we test our agents in multiple ways, right? So if you think about school, maybe we like, maybe we don't like testing, but a lot of us go through a formal schooling system in which there are tests. And these tests essentially guarantee the fact that we are capable at performing our task. And the reason you trust your doctor to make a diagnosis on you more than you trust me is that they have gone for years to medical school and they have been certified through a long series of various kinds of tests for their knowledge. And so my own perspective is that if we want to have real AI agents, we're going to need to devise some way of certifying their ability. And this is actually more complicated than saying, well, the neural network should explain itself, and we're going to look at its weights and try to figure out what the different units do, right? The equivalent of that would be doing an MRI on your doctor and trying to figure out what's in their head. But that's not something that would make us very happy or feel like we're gaining any understanding. On the other hand, putting some work into figuring out how to certify lifelong learning agents might be interesting. The other thing is that a lot of what we do right now is very enthusiastic engineering and very enthusiastic math, and this is also great. But in the rest of science, a lot of the experimentation is actually hypothesis-driven. And so, we might formulate a hypothesis, and then we might run an experiment to test that hypothesis and draw some conclusion. And based on this kind of cycle of experimentation, eventually some knowledge will emerge. But right now, this is not what we do with our agents. We typically try the agent in some environment. We look at what it does. If we like it, great. We put the graph in the paper. If we don't like it, we just look for some other environment. Maybe we cook up some environment where we think our agent is going to do well, and we'll take that graph and put it in the paper. Right? It is not really hypothesis testing. We're not really even formulating hypotheses about what our agents should or shouldn't be able to do. And so I think we perhaps need to take a step back and take it seriously that if these agents are truly intelligent, that we should treat them like we treat psychology experiments or animal learning experiments in a hypothesis-driven fashion. Formulate a hypothesis about what the agent should be knowing by now, try to formally test that hypothesis, and then be patient and see if they're not capable of doing it now, is that going to emerge? And of course, take this information and make better algorithms, but without perhaps so much tinkering with the details of the task. So just to wrap up, I think we have some really interesting, powerful tools for knowledge representation that are coming from the reinforcement learning framework. In particular, generalized value functions are an interesting alternative for representing predictive knowledge that is versatile and incorporates many algorithms as special cases. And of course, the advantage from my point of view is that we have a lot of ways of learning these kinds of representations that we already know from reinforcement learning and we can bring to bear here. There are many open questions regarding this type of representation. Specifically, we don't really know how to generate behavior in the presence of many generalized value functions. Call and return is not necessarily the best way to do it, because if we have tens of thousands of opportunities and options, we need to have some more effective form of search control. There's also still a big question regarding discovery. Right now we're doing things that are still driven by this idea that rewards are going to give us the right structure, but there are very interesting works on, for example, intrinsic motivation that perhaps should be pushed forward. And then I think as a community, we should be thinking about this big open question of how do we evaluate empirically lifelong learning AI systems. I don't really have the answer, but I'd be happy to entertain ideas from everybody. Thank you.
We have time for one question. Excuse me for being so pedantic with time, but I'm guarding the one break that we have with my life.
One question? So if you have multiple value functions, what are you optimizing then?
So right now, when we have generalized value functions, each of them has an objective, which is to accurately estimate its expectation. And if they were to optimize, they would each optimize their own objective. And so essentially, the knowledge becomes compartmentalized. There will be a procedure going with predictive knowledge associated with that procedure that comes out. And so the glue in between, right now we can use sort of usual reinforcement learning methods or planning methods in order to put things together. But like I said, I think there's a lot of open space there as well.
Thank you, Doina.
Thank you.